Thank you. Yeah, I would like to thank the organizers for the invitation, and also, seriously, I want to thank all of you. This is the very, very last talk of the workshop, so I appreciate you all being here. I'm going to talk about Wasserstein 1 distance that we had and some applications, but given that this is the last talk of the workshop, I try to motivate it from a more primal mode, right, and dual mode, which was more advertised during the talks. We already saw some generalization of this distance and also some applications. I'm going to motivate more primal mode and also some applications based on the working groups that we have in the long program. So that's the plan. There's a huge number of collaborators. The original distance was with Giacomo, Dario, and Seth Lloyd. And then the rest, I will talk about some with Bobak, who is in the room, etc. And the main motivation for the start of this was that a lot of distances we use quantum mechanically are unitary invariant, like fidelity, relative entropy, etc. And the moment you have this kind of distance, it cannot distinguish between something like the distance between all zeros to just 1, 1 and all zeros versus all zeros and all ones, the moment you have unitary invariance. And that means that you get rid of the local structure of your Hilbert space. And of course, we like other distances maybe for some applications, like Hamming distance, which is sensitive to these changes. It gives you a number 1 for when you compare this string to this string, and number n if you compare these two, right? So that's the motivation. And we can imagine a lot of situations that will require, go ahead.
What is the distance defined by trace and fidelity? Because the two states you listed in there, the fidelity between them is non-zero. So what's the distance in this case?
Any distance, but fidelity you should define like a distance from fidelity based on that, right? Okay. But even like, let's talk about infidelity, for example, or anything like that. These are all unitary invariant. Just look at the overlap of the states. If you rotate both of them, the overlap doesn't change, right? The overlap of the first state and this one is 0. The overlap of this one and this one is also 0. And that's what fidelity is going to give.
Oh, okay, I'm sorry. I was reading that as one long bit string. I thought, okay, I understand.
Yep, good. But yeah, I mean, I think that's the best case scenario to have some interaction. Again, given that this is the last talk, I feel like I need to make it very interesting. So I tried that, okay? What are the applications? I can imagine whenever you have some local structure that is very important to your problem, for example, you have some shadow depth circuit. You know that the information propagates slowly through your circuit, and you want to have a measure that captures that. Another scenario, maybe you're interested in the entropy of a state. You know that if you're touching a few qubits, the entropy shouldn't jump too much. Or it might be the case that you want to do some optimization task, and your target state has some specific property, the state you want to prepare. Another one is more about error correction and fault tolerance. In a lot of real scenarios, we have some information about how nature is interacting with our system. For example, if we have a good system and we have good control, it's a good assumption that nature is interacting locally with my system. And if I have a distance that keep track of these local interactions, that can be useful for error correction or even fault tolerance. So that's the motivation. And as I said, I'm going to motivate it a bit from, let's say, from a Hamming distance picture. And let's say, how should I think about a Hamming distance? I have a bit string and another bit string, and I want to define the Hamming distance between these two. One way is to just think about how many bits should I flip from the first one to get to the second one. Right? Here, 1, and that's the Hamming distance. But can I do that quantum mechanically? I have 2 quantum states. By the way, in this talk, I'm going to just think about finite dimensional systems. These are density operators, trace one, positive indefinite. And I would like to ask, can I define a distance such that if I act on this state locally, I get to this one? And for example, if you think something like entanglement, you already know that you can't increase some property like entanglement by just local interactions. That already tells you that you cannot get from an arbitrary sigma to an arbitrary rho, right? So that won't be useful. In a sense, of course, we can define, but it won't be useful because you cannot compare two arbitrary states in this form. Maybe we should think it differently and think about going from the first bit string to the second bit string by asking how many bits should I delete, right? I need to delete one, and they become the same. So I say that the Hamming distance of these two bit strings is 1. That seems to work, and I can make it more complicated. Having bit distance between these two bit strings, I can ask how many bits I can delete, or knowing where I'm going, maybe it's another way to do that and just thinking about splitting these differences into a bunch of 1 differences. So I have a Hamming distance 2 between these two. I'm going to compare the first bit string to some intermediate state, or in bit string. And here I have 1 flip, and then another intermediate, this is the same thing as this one, with where I wanted to go. I need two of these operations. I could do this in many different ways, but this is the minimum number of jumps I need to go, and I'm going to define my distance like that. The minimum number of decompositions like this that I need. And this is one way of thinking about W1 distance, Wasserstein distance classically. You can say, I want to now generalize it rather than thinking about bit strings. I'm going to think about probabilities over bit strings. And what I will do is asking how should I decompose a difference of two probability distributions into a convex combination of distributions that are close to each other. In one sense, they are close to each other in the sense that if I trace out one of the variables, if I look at the marginals on the remaining n-1 variable, those are exactly the same. And I ask, what's the best decomposition I can have? And that gives me a continuous version of this picture. And that's actually, you can show that that's one way of thinking about the W1, classical W1 distance. Go ahead.
But couldn't you also think of, okay, I start with my state, and I use some local flips, like some local X gates, and count how many operations I need to reach that?
Classically, yes, but then
Quantumly?
As I said, if to do local operations, you can't go to the
Then if you,
for example, if I start from separable states, there's no way with these operations I can get to maximally mix, maximally entangle.
right, but if you allow convex combinations of those operations, maybe you can.
But convex combination of separables with a state separable, so I don't think it's going to give you an entanglement, right? A mixture of separable states is a still separable.
We can discuss this
Sure,
later.
sure.
It's kind of another intuition, and maybe it actually works.
Maybe.
Let's see, right?
Yeah,
I mean, at
sure.
least this other idea of changing locally and then doing some averages and complicated procedures by local changes and averages, maybe that also works.
One thing in that direction would be the following. You can ask, and actually maybe when I talk about the quantum version, maybe that's, like this is all classical for the second, for this moment. But you can ask, rather than tracing out, what are other channels I can apply on this? And then yes, that's something I wanted to mention. But like this, actually, if we are thinking about like specific local unitaries, et cetera, this is a bit different. So let me continue. I'm going to come back to this point that you can do this quantum mechanically. Now you can think of tracing out qubits, right? And that's a straightforward to generalize to quantum to a quantum setting, and that's exactly what we did. So here, rather than thinking about probability distributions, I'm thinking about the marginals. I'm thinking about tracing out one qubit of two states, they being the same. And then I look at the best composition I can have over this type of states. I'm going to call this a state neighboring. When I have two quantum states that if I trace one of the systems, they become the same. I'm going to call those neighbor states. And I ask, what's the best decomposition of two states that you give me on these neighboring states? Okay? We can make this a little bit more formal. We can think about, again, this definition of neighboring states. We can think about doing this for all the different i's for over in different places in the states, and then look at the convex combinations of those. And that you can define that as being the unit of some norm, and then this distance would be the distance induced by this norm, right? And by this construction, it's trivially at distance already, right? So we just proved that this is already at distance, and we have all the nice properties of it, like triangle, etc., from the distance. But I wanted to emphasize that this is a choice that we are making of this being a trace system. For example, you can imagine that you have other operations applying to both, and then those becoming closer to each other. Absolutely. I think one can show they are equivalent up to some constants Now, with this picture that I started from classical, went to quantum, it should be almost trivial that if I start from two classical states, if you want, states that are orthogonal in some basis, that diagonal in some basis, and I have p's as the diagonal elements being my probability, q being the other probability distribution. If I look at the quantum W1 distance between these two quantum states, it's exactly the classical W distance between these probability distributions, right? With the same picture that we have all been saying for the whole week, right? Which we have a coupling defined by marginals being P and Q, and then you choose the best coupling as the definition of classical basis and distance. And then in the very special case that these are delta functions, these probabilities, you get back the Hamming distance. That corresponds to looking at the W distance of two product states in the computational basis, and that exactly becomes Hamming distance. Any question about the definition?
I think that I have something like related question. So, for example, for data hiding states, like another common task, so what they want to construct is something like two states that they are indistinguishable for any n-1 qubits. That they are very distinguished and they are very far apart as two n-qubit states. So, is there any easier way to construct such a states? I mean, based on this observation? Yes.
Easier, I don't know, but the notion of neighboring states also comes up in this privacy setting, in the sense that you want to make sure that basically you can't extract too much information from these states, and you want to encode information such that when you touch a few of the qubits, then you lose all the global information. So there are related ideas about neighboring states. You can choose, I mean, my philosophy is that you can choose any distance that you want and you can define it. And then the important thing is what you do with it, right? So as long as we can do something interesting, absolutely. Okay. And let me very, very briefly list some properties that might be useful in some application you have. Okay. If you have two neighboring states, one more time, this means that I have two quantum states. I trace out one of the qubits or qubits, and they become the same. The Wasserstein distance between those would be just a trace distance of those quantum states. In particular, this because any single qubit state is neighbor with another state in the same Hilbert space. That means that that is true also for any single qubit. In general, for n qubit system, you can show that it's bounded by trace distance, n times that. So, and given this description that I mentioned about the neighboring states, convex hollow, those, etc., it's very clear that you have these symmetries that don't change the state, right? The index of I, which qubit neighboring states it is, you have this permutation that doesn't change the distance. So you have the symmetries of the distance, which are permutations and unitary operations on local qubits. One property that might be sometimes useful is the fact that if you partition your states into two separate sets of qubits, you get this type of inequality where you can show that the W distance between those two is lower bounded by the vector instance of the two different states that we get. And in the special case that these are product states, this becomes equality. Okay. Now I'm going back to the picture that sometimes we have maybe seen more, is just thinking about the Lipschitzness of a function or operator, that by definition you choose some metric, and then you're asking what's the maximum change the function can have by changing the input. Right? What's the maximum ratio? And that's a dual picture of let's say W distance. You can define it as looking at bounding so that's the definition of the Lipschitzness of function. You can define the W distance by maximum change, maximum difference we can get between these properties weighted to this function, right? It's a dual picture of the W distance. And you can do exactly the same thing quantum mechanically, like just I look at the operators. Here, by X, I mean a traceless operator. It's like rho minus sigma. It's a traceless operator. It's a traceless Hermitian operator, a self-adjoint operator. I bound it by 1, and I do the maximization, and that's the definition of the Lipschitzness of some operator H. Right? This is just definition of states being neighbor. But the nice thing is that you can have an explicit form for this. So this Lipschitzness, we can actually show that it's exactly equal to this particular form, which when you want to calculate the Lipschitzness of an operator, what you do is you compare it to the best thing you can get by replacing one of the qubits with identity and then trying to fill in the rest with your best choice. Basically, what this gives you is saying, what's the maximum change my Hamiltonian, my operator H can generate by changing the state on one qubit or one qubit, right? That's the intuition of this type of term. And you have seen different generalizations based on this definition. For example, in the lightning talks, we were talking, it was basically, there was this alternative definition that you can take the commutation, et cetera, in this definition of the Lipschitzness and then go and see what's the distance you get in the primal form. And one nice thing is that this already gives you a semi-definite program that you can just calculate. Again, the way I introduce it, it becomes almost trivial that for a classical function written as an operator, so here f is an operator, these are the let's say these are some canonical bases, and f is the function that is defining this diagonal of this operator. If you look at what is the Lipschitzness of this operator, it's the same as the Lipschitzness of the function itself. This is something I want to emphasize. This turns out to be very, very handy in a lot of applications. And that is for local Hamiltonians, and by local here, I mean I can write my Hamiltonian as a sum of a bunch of terms. Each one of these terms is only defined non-trivially on a few qubits and acts trivially on the rest of the qubits. So that's the definition of the local Hamiltonian I'm using. And for these local Hamiltonians, you can show that it's bounded by something that only depends on each qubit is talking to how many other qubits using this Hamiltonian, right? It's not an extensive term like what we get for something like operator norm. is something that depends locally on each one of the qubits talking to other qubits. To make it very explicit, and maybe that's the most important thing I want to say about this, is that if you have some geometrical local Hamiltonian, think of a lattice, 2-dimensional, 3-dimensional, and that's the definition of your Hamiltonian with nearest neighbors interaction, etc. This is a constant, which is different than what we get from operator norm, which grows with the size of the system. Okay, why should I care? Because you can also show that you can prove some concentration type results for this distance. What you can show is that if you look at the eigenvalues of some Hamiltonian, they are mainly concentrated in this region. And the important thing is that the Lipschitzness of the operator shows up here. So if you know that this, for your Hamiltonian, this Lipschitzness is small, you know that their eigenvalues are all concentrated around some region. Okay. Up to now, I listed a bunch of properties. Now I'm going to talk about some other properties. I'm going to also talk about their application in various places. One is that we saw that if the states are neighbors, meaning that if I trace out one of the qubits, they become the same. The W distance is bounded by 1. You can ask, what if I trace 2 qubits and they become the same? You can show that we can bound the distance between these two states by something that is proportional to how many things you are tracing out. Right? If you're tracing I of this bound is related to this I. And the consequence of this is that if you have a state rho and you act with some channel phi on the state, which is only acting on, let's say, k qubits or k qubits, it can't go too far. How much it can go depends on how many qubits this channel is acting on. These are the things that we couldn't get with trace systems, because with trace systems, the moment you even touch one of the qubits, it can go as far as it can, right? But this gives you a notion of locality on how far it's going. And this is, for example, asking about the maximum you can do is something that people have studied after this. It's like quantum Wasserstein complexity. I know that Marius also has worked on it. Seth and Quadras have worked on it. The other property that I'm going to use later is contraction coefficients. And this is asking if I have some quantum channel, some CPTB map, and I start from two different quantum states, rho and sigma, the outputs of this quantum channel, how far they can be in this distance. So phi rho, phi sigma, these are the outputs of the channel. I look at the Wasserstein distance of that and compare to the Wasserstein distance of the inputs. And you can look at the maximum of that. And one thing you can show is, again, it depends on the light cone of this channel. Light cone basically means if I touch one of the qubits on the input, how many qubits on the output of the channel will be changed. Okay? So it gives you a bound on that. I want to talk about that a bit more. This is also very, I think, interesting. So this is the same thing I showed in the previous one. And a consequence of this is that if you have some state rho and you're acting with a bunch of different channels, phi 1 up to phi m, and you look at the output and you call it rho out, and then you input another state, you call it sigma, and you look at the state that you get, you call it sigma out, and you ask what is the difference between the Wasserstein distance of this compared to the Wasserstein distance of the input. You can show that this is a constant independent of the number of qubits, independent of how many things I'm putting here. Okay? So it's really about the light cone of things rather than the number of qubits you have. Again, these are some things that I emphasize in case it shows up somewhere and I feel like you need some mathematical tools to help with those. Maybe this kind of distances are useful. Not only this one, but just generally this kind of distance.
What if I replace the local Hamiltonian? Like it's not a two local. Like, for example, I have an H is KL local, and I run a
Yeah, so you can have a continuous version of this as well, like LibRobinson.
Do you imagine this can be exponential in k or decay, linear decay?
I don't know. I should think about it.
I just
Yeah, I
just
can.
want to know what's your answer because I think this is exponential decay.
So this I don't know, but the important thing is I expect that the dominant term is going to be independent of n still.
Yeah,
So,
of course.
yeah. Let me move on. A very in particular version of this that turns out to be very useful is that I'm using the same channel over and over. And I ask about the contraction coefficient of tensor of channels. Again, this is something that if you think about the tensor of channels, if this number of channels goes to infinity, if you use something like trace distance, and you compare n copies of the first state with n copies of the second state, it always goes to 1 because it becomes more and more distinguishable if you want, right? That's one way of saying it. And so you can't have a very meaningful output. It's just independent of the channel you will be using. But if you use a distance like this, you can show that actually you can get bounds independent of n. For example, you can directly calculate for amplitude damping, an example of a physical process, a physical noise process that's very useful. And you can actually bound this as a parameter of the amplitude damping, similarly for depolarization. So I promised applications. I'm going to list a few applications. The first one is continuity of entropy. If I have some quantum state and I touch just k number of qubits, I don't expect the entropy, the entropy of this state to change too much, right? It will be proportional to how many qubits I'm touching. And the question is, can we do something non-trivial for this using the W distance? And actually you can. So you can show that you can get some non-trivial bounds on the difference of the entropies in terms of the W distance. Classically, you can also do the same thing, and that's actually how we started doing this. One thing to emphasize is that, and I'm posing this on an open problem, we have a log n in our continuity bound for entropy that is not, that we couldn't get rid of. We know that this classical version should be modified for the W distance, but whether you need a factor of n or a constant, that's not clear. Okay, so it's an open problem that I wanted to mention. You can define a quantum Martin's inequality, which basically relates the W distance to relative entropy. And basically, you can perfectly recover the classical version of that. OK, so that was the first application about continuity of for Neumann entropy and also relative entropy with respect to product states. And now I want to talk about, I have 20 minutes, right? 25, 20, good, good. Any question before I move on? OK, so now I want to talk about the second application. It's going to be a little bit of detour, and then I'm going to come back to the distance, OK? And that is thinking about quantum algorithms in general. Usually the picture is that I start from some states. I apply a bunch of gates and perform some measurement. And if I've designed my algorithm well, this set of gates is going to do what I wanted. And hopefully this is efficient in the sense that the number of gates I need to apply is some polynomial function of the input size of the problem I wanted to solve. And unfortunately, devices, we are not there yet in the sense that for a lot of practical applications, the number of qubits and the quality of the operations we need, the size is very limited, the operations are very noisy, and we are not there yet. And we want to ask, what about limited cases? What if I only have access to a limited number of gates, for example? What can I do with them and what I cannot do with them? Okay? So, I mean, it's a practically motivated question, but also fundamentally we want to ask what's the power of a limited quantum circuit. And the specific limitation I'm going to focus is I have a bunch of qubits, n, and I'm only looking at number of gates that is slowly growing in the number of n. So it's very shallow, the circuit that I'm going to apply. Okay? And we want to ask what's the computational power of those circuits. One strategy that people have tried is that designing new algorithms with this type of limitation, saying that, oh, you have access to a few qubits with a few gates. Let's add on some classical computing power to your quantum computer and, for example, do operations hand in hand between the two. For example, one specific family of algorithms, variational algorithms, where you parameterize your gates, you perform your circuit, and you do the measurements, and you calculate the cost function, and you update using some optimization technique the parameters of your gate, and you repeat, and you hope that you solve the problem you want. A very specific algorithm in this family is one that you choose the gates in a very particular form to perform optimization. So you have some optimization cost function, and the algorithm says, start from some state, basically apply this cost function as a Hamiltonian, evolve it, and then do something that mixes all the bit strings to each other with some parameter, do another round of this, another mixing, and repeat this bunch of times. This is supposed to be measurements. For some reason, PowerPoint is changing my measurements to this, and I corrected this once before. I don't know why it's jumping back. But these are measurements. You perform some measurements, and then you do the cost function, and you optimize. Here, the parameters are lambdas and betas, and then you repeat it. You repeat this, and you hope that your optimization works.
This configuration is also very often appears in oracles, right? You have an oracle, you do something in between. You do
Absolutely.
So it's very...
Absolutely. And very similar to that, the question here, for example, would be how many layers of this do I need to use, which is, in that context, might be about how many calls to the oracle unit, for example.
Oracles, there are some bounds for those.
Yeah. So here, one important parameter that I want to emphasize is not the layer of this, and this, which I call P here. How many layers do I need to perform my task? Bunch of I want to make it very clear that in general, doing this optimization is NP hard for arbitrary function, for arbitrary classical function, and we don't expect quantum algorithms to give us substantial improvement for NP-hard problems. Okay? We might hope that one finds subclass of problems that quantum computers do better for optimization, and that's an active area of research. And then there are a lot of challenges with this. For example, you can think about this optimization task and how hard this optimization is. For example, there's this phenomenon of barren plateau, like how easy it is to find the gradient of this direction that you want to go. Or actually the landscape, for example, work what Bobak did, like they look very, very ugly in the sense that they have a lot of local minimas. And then, so these are challenges that this type of algorithms need to, they face. I want to look at one specific family of optimization problems that people have looked at before, and that is called max cut. Just to give you a notion of what kind of problem is, what's the cut is coming from. You're given a graph. You want to partition your nodes into two different partitions such that the links between the two partitions or the edges between the partitions are maximum. If you don't like that, you can just think it as optimizing or maximizing the energy of this Hamiltonian. Here, sigma z is Pauli z. You can think it as a classical variable taking values +1 and -1. And your goal is to find these assignments such that the energy of this Hamiltonian is maximum. The interaction between this and where they're defined is defined by the graph. E is referring to the edges of the graph. As I said, this problem can in general be hard, and we might hope to find interesting classes of problems that we can do better than classical algorithms using this. But there was this very interesting paper by Bravi et al. Where they showed that actually for a very trivial problems of this form, this QA algorithm is going to fail if the depth of the circuit is not deep enough. Deep enough exactly is log n being the number of qubits I started from, and log n, if the depth of the circuit is smaller than log n, you can prove that even for these trivial problems, the QA algorithm will not beat existing classical algorithms. So it's a provable no-go result, okay? And I'm gonna spend a slide on reviewing what they have done, and I'm gonna exactly ask what properties they need, and then I'm gonna go back to the distance we introduced and see what we can do with that, okay? So bear with me for another slide on this specific problem, and then we're gonna go back to the optimal transport, and we would be happy, okay? The specific graph they introduce is is a D-regular, meaning that the degrees of the nodes are D, it's bipartite, and it has this property that is expanded well, meaning that if you look at any subset of nodes here, for any of those, they're connected to a large subset of nodes in the other side. Okay? For this specific graph, they show that if you want to find high energies of the Hamiltonian, and this is a very weird function, I'm going to get back to that. The details of that is not important, but the high energies of this Hamiltonian, whatever algorithm you are using has to do this specific task, which is generating samples from two set of beta strings, which are far away from each other in the Hamming distance, but the probability of each one of them is not negligible. Like at least, for example, you need to generate samples from this box with probability 1/4, from this box with 1/4. But the challenge is that the Hamming distance between these is a function of n. That's what they did, okay? And I won't explain it, but they show that if you want to reach, you want to generate a space with that has high energy enough, you have to do this. This is very similar to what Bobak talked about, which is about the bottlenecks, if you remember from his talk, where he was thinking about the mixing time and having the bottlenecks and having these projectors and transition, etc. But this looks like a bottleneck because you have something that you want to generate proportional by n. But the important thing is that it's coming from the symmetry of the problem. The fact that you have two different regions is coming from a very particular property of this algorithm, which is actually, if you look at it, everything commutes with x tensor n. It has a very particular symmetry that if all zeros are the solution to something, all ones are also solution to it. It has this symmetry. Okay? So this bottleneck is introduced by symmetry as opposed to what Bobak was talking about, which was like you had it for random graphs and like for different regions of general graphs, etc.
So the graph is very connective, or what are the properties of the graph for this?
So this graph, the properties are expanded. So in addition to,
okay.
Yeah. Now, what they show is that to reach this, or basically to satisfy these two properties of having high probabilities on two far away regions, the depth of the circuit has to be at least logarithmic in n. Okay? So that's what they did. That's basically the summary of what they did. Just let's plug in some numbers. If you pick d, the degree of the graph, and you plug it in here, let's pick it to be 55, you can show that when you plug in this specific number, you hit a ratio that we already have classical algorithms that can do better than this ratio. So for any d larger than this number, we know that they cannot beat the best classical algorithms we already have. Okay? Just as a teaser, you can ask if I choose 55 and I want some non-trivial depths, for example, depth 1, how many number of qubits do I need? And it's 10 to the power 54. Okay? So it's a theoretically interesting result, but it's not like really ruling everything out. These constants matter. Now, as I promised, I'm going to go back to our W distance. And what we do, we say that, oh, we can actually do something related to what we were doing about the Lipschitzness. We can think about proving some Poincare inequality, thinking about, first let me define it. We say a state sigma satisfies a Poincare inequality with a constant C if for any observable O, the variance of this observer with respect to this state is bounded by a constant that is independent of O and sigma times the number of items that I have times the Lipschitzness of the operator. Importantly, this C needs to be independent of the observable and state. What we prove is that using this W distance, actually you can bound this C, and you can show that actually, as we expect, is related to the light cone of the quantum circuit, this coefficient that we have in this Poincare inequality. So basically, we are saying that if you have a limited depth for your quantum circuit, the variance of the states that you can generate and the distributions you can generate will be bounded, right? So that should give you an intuition that the probabilities that you can get are very like, it can be too much spread out with high probability, right? It's the opposite of what we wanted for that problem. So if you plug in the numbers, you'll see that actually you can show bounds that actually are, as a function of d, are logarithmically better than what I showed before. For example, if I do the same thing with 55, now you get to the region of million numbers, like 10 to the 6. Let me compare to the previous case. There's this logarithmic difference in d, and there's some coefficients are improved, and you can improve it from here to here. This is more like, I'm talking about an application, but in my opinion, this is more like a general power of this type of approach is like thinking about geometry and thinking about how you are limiting the variance, etc. Okay? So I don't want to overemphasize those numbers. This is the key point.
Any chance of moving the degree inside the logarithm? Maybe with a minus. Log n minus log d.
Oh.
Or log n minus. Yeah.
I need to think about it. I don't know.
Why did you?
Go ahead.
Why didn't you use the contraction coefficient?
I'll talk about contraction coefficients as well.
I'm asking, why didn't you use contraction coefficient to prove lower bound for this model? Because, as you said, the contraction coefficient also has a lag cone.
Yeah. I don't know about it. Like, I don't remember that we compared the numbers or not. So I don't know. It might be that it gives you a better answer or not. Yeah. I'm going to come back to contraction coefficients in a second. But is the story here clear? I guess this is an important point I wanted to emphasize. One more application, and we started 5 minutes late. I see, that's why. Good. Is something I promised about optimal control. So one thing we can do is thinking about the landscape of this optimization that we have to perform. Imagine that my goal is to generate some state. This is called a GHZ state, Neumann state in some community. It's just a superposition of all zeros and all ones. And it's very useful for a bunch of applications, sensing, etc., metrology. And let's say my goal is to just generate this state. And I'm going to handpick this specific quantum circuit to generate this state. And what I'm going to do is generate this state variationally. And I'm going to look at the state and compare it to this GHZ. And look at what kind of result I get. And I continue my optimization and see what kind of landscape I get and whether I can generate this state or not. Right? That's usually the task in optimal control. You want to generate a fixed state or fixed unitary or fixed operation. You have some cost function and you optimize what you have, the parameters you have in your system to get to where you want to go. And let's say if I choose my fidelity as my cost function, you can show that actually the gradients for this specific circuit is going to decay exponentially. All right? So as you scale up this problem, you won't have a nice landscape and you will have problem finding the gradients of the problem. But what it can prove is that if you use something like W distance, as you move on and you create more states, there's a procedure that you can show that you are directly getting closer where you want it. And actually, you can perform some simulation and actually see that if you look at the success probability, if you use something like fidelity, you have some decay, and then if you use this kind of Hamming distance or Wasserstein distance, you continue with high probability generating the state you wanted. This is a toy example in the sense that we handpicked this. The claim is not that it's going to work always, but it's just a showcase of a toy problem that you can prove that for specific states, the landscape might benefit from the knowledge that the state you want to prepare has something about Hamming distance, for example. Okay? We can, of course, have fun and play with more general random states, but we can't necessarily prove things. And then we look at what classical literature people have done. For example, there's this concept of GANs, where to generate the states, in this case, if you want to generate a phase, you let two neural networks compete to each other. And the first neural network, the generator, generates some phase. You compare it with some real phases. And if the other neural network, which I call discriminator, cannot distinguish these two, you have succeeded in generating phases very close to what you want. This is very actually applicable if right now you go to this website, this person does not exist, and you click, it generates a face of a person that does not exist, okay, as it should. And they usually use this algorithm. And this is just motivation of some numerical simulations to see how far we can, this property of this landscape, how far it exists. And you can do the same thing quantum mechanically. You can have a generator with fixed architecture. This is not handpicked anymore. It's like some fixed architecture you choose. You have some parameters here. You generate some state. And you compare it to the state you wanted to generate. For example, in the previous case, this GAC. This is your real data if you want. And this is the thing that you're faking. And the task of discriminator is to distinguish these two by performing measurements on these two states and see is this one or that one. And the important thing here is that now you can use the Lipschitzness of the operators here. If you use these measurements that you perform to be Lipschitz at most one, you're basically, in the limit that you do the optimization, you're recovering the W distance. And you can do numerical simulations. Actually, all credits of the simulations go to Bobak. And yeah, I mean, you see that in a lot of cases, you have much better improvement compared to something like fidelity. Okay? I want to emphasize that I don't expect this to work for general states. This W distance being a number between 0 to n, and the size of the Hilbert space being exponentially growing, it already tells you that it has a very limited power in what it can generate or not. But the problem is that, or the question is that for the problems of our interest, are there particular subsets that can be helpful or not? Okay, so it's just motivating. the last thing I want to talk about is fault tolerance and error correction. It happens, so life happens, errors happen, and we have a bunch of qubits. Let's say each one of them go through some error process, and then we apply some gate, we have some other error process, and we continue that. And actually, there exists a theory of quantum error correction and fault tolerance, which guarantees that if you pay enough overhead, you can deal with the noise of this form as long as your noise is not too high enough. There's a threshold theorem. But we don't know what this value exactly is. We know we have constructive methods that we have shown that if the noise is below this number, I have this construction, you add this extra resources, and you can simulate the quantum algorithm you had for arbitrary long time, for example. But we don't know exactly how much we can push that. So it's nice to have things that upper bound this and lower bound this threshold, right? And this, we don't necessarily have enough tools, in my opinion, to ask the following question. I start from n qubits. I apply gates and also noise. And I want to see how long I can carry on my calculation. When the channel is unital, is unital because, for example, it's entropy non-decreasing, you can show that entropy measures like relative entropy, et cetera, are very handy. And for specific channels like local depolarization, you can already show that after logarithmic depths, your computation will be washed out by noise. So the model is that I start from some number of qubits, I have noise, and I can't add ancilla or anything like that in the middle of the computation. I just started from some number of qubits and everything's going on. And you can show that for a specific type of noise, basically output of the circuit becomes independent of the input. That's one way of thinking about it, and therefore you can't do any useful computation more than log n depth. But what about other channels? First of all, we don't have enough mathematical tools. And weird things can happen with non-unital channels. One interesting thing is that with non-unital noise, what you can do is to create ancilla middle of the computation and use that to correct errors as you are going on. So you can show that you can use your quantum computer as a refrigerator if you want to prepare ancillas and continue the computation. But let me see what our Hamming distance and Wasserstein distance can tell us in this case. We had two observations about contraction coefficients. One, the contraction coefficient of tensor of channels is independent of n. And for some cases, we could easily compute it, right? Like depolarization, amplitude damping, et cetera, that I showed. And the other is that if you have layers of channels, it only grows as a light cone of that, right? We showed that this is something we walked through together, is that because of the contraction coefficient, this can only increase as a number of gates a number of qubits that each gate touches. And I can just combine these two. So I can start for a channel that is like a layer of unitaries, and then a layer of noise, and a layer of unitaries. I can just combine this contraction coefficient and multiply them together. And what you get is actually, you can show, and this is not a work by me, actually, it's by Daniel and co-authors, which you can show that you get this exponential function of depths again, L, the depths of the circuit. And the moment this number is smaller than 1, you are guaranteed that exponentially fast in L, your output is becoming independent of your input, and therefore you cannot do useful computation after log n, right? So they actually do this characterization for single qubits, right? We know that single qubit channels, we have a very precise characterization of these. And you can bound the contraction coefficients based on this characterization. And you get some numbers. And when you calculate the numbers are not So that's excellent. So we have new tools, but the numbers can be like the noise level should be 95%, right? So it's not necessarily very informative too much. The reason I'm saying this is that it's a new tool, but these factors of 2 or not that we use in defining the distance, and sometimes we don't care. I say that, oh, this is the same. This distance is equivalent to this distance up to a factor of 2, and like or constant, etc. Those type of things matter here. If the noise is divided by 2 and it's coming from 95% to 45%, it's a huge difference. Like it gives experimenters a heart attack when you like ignore these factors of 2 because we spend a lot of. It's very hard to reduce the noise of these things, right? So I just want to say that it would be nice if our mathematical tools also capture this kind of behavior, right? This is a lovely paper I encourage you to read from Daniel. And with that, I'm done. So these are the things I covered. And also there were already applications about learning, gives a state that Daniel presented, about lower bounds of open systems that Marius and work. So there are a lot of other applications. I just cherry-picked a few of those that I talked about. I want to acknowledge all of my co-authors and also the funding agencies.